recursive one is the final one left. Okay, so if I just remind us of a simple way of creating our sum algorithm, okay, and it's going to be kind of vaguely in Python. So if our sum has become equal to 1, we just return 1. Else we return, and it's recursive, so we need to have, well, n plus the sum of n minus 1. Okay, and that's should be pretty close to valid Python. Just as a reminder, in our recursive terminology, this was our base case. Remember, when we create a recursive algorithm, we need to have base cases. Okay, and then we have we can have one or more base cases, of course, and we can have one or more recursive cases. Okay, and you can see if we maybe, instead of just saying case, recursive step, we'll see how this actually, when you express things using recursion, it is incredibly close to induction itself. Okay, because we already have a base case. We already have a statement of saying what happens in a very simple example if n is equal to 1. So if you use your induction mindset now and reread this code, you'll see, or hopefully you get the idea, we're saying in a very simple case, the sum of n, if it's 1, will be 1. Okay. Now, in our recursive mindsets, we've always thought of this as our algorithm has been recursing for a while. We hit a base case, we stop recursing, and we return the answer. All those calls then fold back, and we should get the sum being returned. Okay, now when we look at it with our inductive mindset, we can see there's a very close relation. So if we follow the same pattern, we have our base case. Now, instead of calling it sum, we just use the same consistent terminology. Okay, well, in this case, the algorithm just returns 1. Okay, so the base case of this algorithm returns 1, which is as the source code says. So it's very convenient. Okay, and then if we look at the inductive case, okay, well, then we say, well, we change our variable to k. And what's that going to be? Well, we just look at the recursive line here, and that is basically we'll return k plus p of k minus 1. Okay, and then we can basically say, well, this is a true statement. Okay, so the arithmetic sum of 1 is indeed 1. We return that in our base case. And in the inductive case, when we still have, we want to go further, we have the statement, well, we should have the arithmetic sum of k is going to be k and every smaller number before it. Okay. So then if we take a step forward, plus 1, that is going to be k plus 1 plus p of k plus 1 minus 1. Again, got to remember everything here. And when we tidy this up, it's sort of have to sort of squint to see it, plus p of k. Okay. So this is already true. Okay, we already have made the statement that p of k is true. So the next step, k plus 1, well, k plus 1 plus p of k, which is already true, will give us the sum. Okay, so it's practically like we're writing out the source code when we're doing this in the recursive, with recursive formulas, so our functions. So it's really pretty much the same. Okay, so there's a really tight relationship between writing recursive functions and actually already having a proof. Okay.